Hello students, welcome to YourPedia video classes. This is Sekhar, a senior faculty in mechanical engineering. In these video lectures, I am going to cover the very most important questions pertaining to the ISRO 2023 examination, which is going to be conducted after few months or after few days. Okay. This, as you are aware, this year the pattern of examination for the ISRO 2023 is different, entirely different from the previous pattern. So the video lectures what I am going to give is corresponding to the new pattern, and while covering this subject called most important subject in the ISRO examination called heat transfer, I am going to cover the heat transfer subject. By solving the most important questions, I am going to make you understand the concepts of this subject, because this subject contains 4 important chapters: conduction, convection, radiation, heat exchangers, and of course a small topic called boiling and condensation. So that is a very small topic. So in these 4 chapters the questions may be equally distributed. That is what we have seen in the previous ISRO papers also, but this year the pattern has been changed. So one question 1 mark, and each question must be solved in a time span of around 1 minute to slightly more than 1 minute. Okay. So you should be able to understand that thoroughly the concepts, and we have to use those concepts to attempting the question in the quickest time with the utmost accuracy. So after seeing my videos, definitely I can make you assure that all the concepts you will be connected. All the concepts of the heat transfer will be well connected, and you would be able to answer the question in the quickest time. In fact, the heat transfer subject, why it is important in the space applications is rocket propulsion, jet propulsion, and particularly the most important mode of heat transfer called radiation. That is very important in the space applications. In the BARC examination, DRDO examination, ISRO examination, this subject plays a very important crucial role. And I am going to solve approximately around 100 questions of heat transfer. I have selected a good typical type model questions which were asked conceptually. So by each question I will be solving by explaining the concept behind the question. So you must be able to understand those concepts thoroughly after completely watching my videos. In fact, these videos would be available in the YourPedia website or YourPedia panel, and after watching the videos, you will definitely feel that yes, I have learnt a good concepts in this subject. I would be able to face the examination confidently. That feeling definitely you would get after seeing my video lectures. In fact, I am going to in detail explain the most important topics selected for the questions. For example, if the conduction is there, I have selected the important topics like critical radius, unsteady state, lumped heat analysis, Biot number, okay, and fins and composite structures, heat transfer through composite structures like slabs, cylinders, and spheres. So all these important topics I have selected and framed a question in those important topics and explained thoroughly. While solving the problem, you would be able to understand the concepts. So welcome to this video lectures, and you can watch these video lectures in the YourPedia website or YourPedia panel. So welcome to these video lectures of heat transfers. So the first question goes like this. I am going to give the concept and as well as solve the question. For heat transfer across a composite slab with materials having different thermal conductivity, study the following statements. This is a very first basic case study of the conduction heat transfer. The question can be solved like this. If you just draw the temperature profile for a composite slab containing 2 different materials, the temperature profiles will appear like this. This is temperature T1, right side temperature is T2. This is the interface temperature or junction temperature, T interface or junction temperature. T1 being greater than T2, this is the direction of the heat transfer rate. This is how the heat transfer is happening along this x direction. Okay. Now, if we just look at this particular temperature profiles, I am assuming the thermal conductivities are constant, but two different materials, therefore two different conductivity values. First of all, we should know that thermal conductivity is a material property, one material, one value of K. Of course, in this particular one-dimensional steady-state conduction heat transfer through a composite slab, I am assuming the thermal conductivities are constant for a given material, but once the material changes, conductivity value changes. So this is how the temperature profile looks like. This is how the temperature drops along the x direction. T1 greater than T2, therefore this is the direction of the heat flow. What are the things you can infer? What are the things you can understand from this temperature profile? Just by saying that, I can say that K1 is greater than K2. One thing you can easily interfere that. Okay, you can infer that, you can understand that K1 is greater than K2. Why? Because if we just look at the slope, dt by dx here and here, dt by dx value, dt by dx value is lesser here, here it is more. From the Fourier law of conduction, Q is equal to minus Ka dt by dx. dt by dx is called as the temperature gradient. For steady state one-dimensional heat conduction equation, this is the Fourier law of conduction. Fourier's law of conduction. Okay. This Q is same all along both the composite slab. This Q is same throughout. Q will not be different. Whatever the heat is conducting through this, same heat must to satisfy the steady state. Steady state conduction means what? Steady state heat conduction means temperature at a particular location must not vary with respect to time. Temperature is not a function of time. This is the meaning of steady state heat conduction. Therefore, Q is same throughout. Q is same throughout. Whatever the heat is conducting through the first slab, same heat must conduct through the second slab. That is one thing you can understand clearly. And Q is same throughout. Area of heat transfer is also same throughout. For any slab case, for any composite slab case, area of conduction heat transfer will not change in the direction of the heat flow. It remains constant. Q is same along the x direction. A is also same along the x direction. But this dt by dx, if we just look at this dt by dx here, this dt by dx here in this first part of the slab is lesser. You can see that the slope of the temperature profile, the temperature gradient is lesser here, here the temperature gradient is more. Because dt by dx is lesser here, K value must be more. That is why K1 is greater than K2. That is one thing you can infer or you can understand from the given temperature profiles. So, but the question is something else. What is the question asked is, temperature is continuous always? No, it is not. It is not continuous. See, look at this. There is an abrupt change in the slope here. The temperature value of temperature begins to change abruptly in the second part. Temperature is not continuous. So, the first option is not correct. Look at the second one. Temperature gradient is not continuous. Yes, that is correct. Temperature gradient is not continuous. If you just look at this, temperature gradient is different here, it is different here. Temperature gradient is not continuous. Second option correct. Third, if you just look at the third one, heat flow is not continuous. Heat flow is continuous. It is not. That third option is wrong. Why heat flow is continuous? At any x, the value of the Q is same. Why? To satisfy the steady state conduction heat transfer condition, the Q value must be the same. Therefore, my only one option is correct. Temperature gradient is not continuous. So, the thermal circuit, if you just look at this, for this situation, this is the thermal circuit. The heat current is same throughout. Steady state heat flow is same throughout. This is the interface, temperature interface. This is the first thermal resistance. It is given by B1 by K1A. This is given by B2 by K2A, where B1 and B2 are thicknesses of the slab. A is the area of heat transfer, which is same throughout. The Q is same throughout, therefore the third option which is given, Q is not continuous, that is wrong. So there is only one option correct, that is temperature gradient is not continuous. Why temperature gradient is not continuous? dt by dx changes abruptly with respect to x. That is why temperature gradient is not continuous. That is a correct option for the first question. Look at the second question. For a specified inlet and outlet temperatures, for which kind of the heat exchanger will be the log mean temperature difference will be the highest? LMTD, log mean temperature difference, one of the most important term in the heat exchangers. Whenever you study the heat exchangers chapter, there are two important terms we should always keep in mind. Number one, LMTD, that is log mean temperature difference, and number two, effectiveness. Any question asked in the heat exchangers is pertaining to either LMTD or effectiveness. This question is regarding the LMTD. So where that LMTD will be the highest? As you are aware, there are three kinds of heat exchangers generally we deal. One is parallel flow type of heat exchanger, second thing is counter flow type, third thing is a cross flow heat exchanger. There are three different types of heat exchangers, out of which is said to be thermodynamically most efficient, that is counter flow heat exchanger. Why? Because why the counter flow heat exchanger is supposed to be thermodynamically most efficient? Because for any given inlet and exit temperatures, the LMTD value for the counter flow heat exchanger is maximum among all the heat exchangers. I could explain you like this. For any given inlet and exit temperatures, the temperature profiles go like this: THI, THE, with standard notation. What are the standard notation? THI means hot fluid inlet temperature, THE means hot fluid exit, TCI is the cold fluid inlet, TCE is the cold fluid exit. This is a hot fluid temperature profile, this is for the cold fluid. In this figure, both the fluids are commuting or traveling along the same direction, therefore it is parallel flow heat exchanger. If we just draw the temperature profiles for the counter flow heat exchanger, the temperatures would vary like this. For the hot fluid, this is the temperature variation, THI. Among the four temperatures, which is the highest temperature? Hot fluid inlet. This is THE. This being the counter flow heat exchanger, cold fluid will be traveling or commuting in the opposite direction to the hot fluid. Therefore, this is how the cold fluid temperature is rising. This is TCI, this is TCE. This is for the counter flow heat exchanger. Okay. This is delta Ti for the counter flow. So in counter flow, delta Ti is the THI minus TCE. Whereas in the parallel flow heat exchanger, delta Ti is THI minus TCI, delta TE is THE minus TCE. Okay, please notice that the delta Ti and delta TE definitions are different for the parallel flow heat exchanger and for the counter flow heat exchanger. Here the delta Ti means THI minus TCI. Here the delta Ti means THI minus TCE. Here the delta TE means THE minus TCE. Here the delta TE means THE minus TCI. That point we have to clearly keep it in mind. But even though the delta TA and delta TE definitions are different, the LMTD formula for both the heat exchangers, it is same. That is given as delta Ti minus delta TE divided by ln delta Ta by delta T. You should always use the natural logarithm. Ln means what? Natural logarithm, that is log base E. Okay, this is the LMTD formula for both the heat exchangers. Same formula for parallel flow and counter flow heat exchangers. But the definitions of delta TA and delta T. If we just calculate for any heat exchanger keeping the same 4 temperatures in both the cases, you will definitely see that LMTD value is more in counterflow heat exchanger. That is why the thermodynamically, which is more efficient heat exchanger, counterflow heat exchanger. I can say for any given heat transfer area between parallel flow and counterflow heat exchangers, you may expect more value of the heat transfer rate between hot and cold fluids in case of counterflow heat exchanger as compared to the parallel flow. For the same heat transfer area provided in both the heat exchangers, you may expect more LMTD value in more heat transfer rate in counterflow. For the same heat transfer area provided, this can provide more heat transfer rate. Why? Because this delta T being more in counterflow, the value of the heat transfer rate also will be higher in counterflow. Okay, and I can say same rule for the cross flow also. Even counterflow is more than that of the cross flow. I can say for the same inlet and exit temperatures used in all the 3 types of heat exchangers, that is parallel flow, counterflow and cross flow, the LMTD values change like this. LMTD delta Tm of the counterflow is greater than delta Tm of the cross flow is greater than delta Tm of the parallel flow. So this is the descending order of the LMTD values when all the 4 temperatures being used same in all the heat exchangers. I repeat once again, when all the 4 temperatures being same in all the 3 kinds of heat exchangers, LMTD value is highest in counterflow, least in parallel flow, and cross flow is via media. So that statement I could definitely I could give it, and we must remember that particular descending order. Supposing sometimes he has given the shell and tube condenser, that will come just before the cross flow. Shell and tube condenser is also a cross flow, but whenever there is one fluid is condensing, I remember whenever one fluid is condensing, in such case the capacity rate ratio value becomes 0. So such heat exchanger definitely would be having more LMTD and higher effectiveness. Supposing if it is given 4th heat exchanger in the name of the shell and tube condenser, that would fall just before this cross flow. Okay, so that descending order one should not forget. So that is the reason why for a given heat transfer rate, counterflow heat exchanger occupies least area. That statement also you must remember. For given heat transfer rate required, counterflow occupies least area. It is the most compact heat exchanger. Counterflow heat exchanger requires least area. Counterflow heat exchanger requires least area and most compact in size as compared to the other heat exchangers, because it has got the highest LMTD for a given heat transfer rate. Because the delta Tm value is more, LMTD value is more, highest in counterflow, area will be the least. Where what is the U? Overall heat transfer coefficient, U, having the units of watt per meter square Kelvin. So this is a very important question that answered like so. LMTD value is highest in counterflow. Okay. The next question: what is the Prandtl number for a gas at 27 degrees Celsius and 1 into 10 power 5 pascals with kinematic viscosity equal to 1.8 into 10 power minus 5 meter square per second, specific heat capacity Cp value is given, and thermal conductivity of 0.02 watt per meter Kelvin. Take gas constant as 300. Prandtl number, the most important number in the convection chapter. Prandtl number is the only dimensionless number which is a property of the fluid. In convection chapter, we come across so many numbers like Nusselt number, Reynolds number, Prandtl number, Grashof number, Rayleigh number, Stanton number. So many numbers we come across. But among all these numbers, I can say there is only one number which is a property of the fluid, that is called as the Prandtl number. defined as the ratio between Prandtl number PR. I am writing the formula. Prandtl number is equal to mu Cp by K. Okay. But while using this equation, one must be extra careful that mu should be kept only in Pascal second. This Cp should be kept in joule per kg Kelvin. Joule per kg Kelvin. This thermal conductivity must be in watt per meter Kelvin. Then only it will become the dimensionless number. Prandtl number is the ratio between kinematic viscosity divided by thermal diffusivity, nu by alpha or mu Cp by K. Fine. But here for the gas to calculate the Prandtl number, we should know the value of mu. But dynamic viscosity mu is equal to density into kinematic viscosity. Okay. He has given the kinematic viscosity, but I don't know the density. How to calculate the density? We have to assume that gas is an ideal gas, and from the given value of the temperature and the pressure, you must calculate the density. Ideal gas equation or perfect gas equation, ideal gas equation or perfect gas equation is given as P by rho is equal to RT, or rho is equal to P by RT. What is this R? R is the characteristic gas constant which is given 300 joule per kg Kelvin. This is the R. Okay, R is given, pressure is given, temperature is also given, but of course it is given in Celsius. We have to convert into the Kelvin. From that we are able to get the density which is in kg per meter cube. First let me get the density there. Okay. Rho is equal to P by RT. P is 1 into 10 power 5. R is taken as 300. Temperature is given as 27, but we have to convert into the Kelvin. 27 plus 273. Okay, 27 plus 273. We have to keep this temperature only in Kelvin scale always. So you got the density as 1.111 kg per meter cube. Now you got the density. Then Prandtl number PR is equal to mu Cp by K, density into kinematic viscosity into Cp by K. 1.11 into kinematic viscosity kV is given as, for the gas, 1.8 into 10 power minus 5. The specific heat at constant pressure is given as 700 joule per kg Kelvin divided by thermal conductivity is given as 0.02. You will get 0.7. 0.7 is the answer for the Prandtl number for the gas. Mostly it should be air. Mostly the gas should have been air, because for Prandtl number value for the air it will be 0.69, 0.7 like that. Okay. Prandtl number is a property which is a function of temperature again, but for one fluid we can consider the Prandtl number as a one value. Okay. This is how the third question has been done. The Lewis number, yes, one of the another important dimensionless number. The Lewis number, which is a measure of relative thermal and concentration boundary layer thicknesses, is defined as Lewis number, which is also a dimensionless number, is the ratio between Skint number divided by Prandtl number. Skint number divided by Prandtl number. First, in this particular question, we come across three different numbers: Lewis number, Skint number, and Prandtl number. Let us understand the three numbers independently. Prandtl number. It is a ratio between kinematic viscosity divided by thermal diffusivity, nu by alpha. This is the Prandtl number definition. Here there are two properties of the fluid. One is Kv and other is thermal diffusivity. What is Kv? The nu, Kv nu is equal to dynamic viscosity divided by density, having the units of meter square per second. What is this alpha? Alpha is called as the thermal diffusivity. Alpha is a thermophysical property of the fluid. Thermal diffusivity defined as the ratio between thermal conductivity divided by thermal capacity. K divided by thermal conductivity divided by heat capacity or thermal capacity. This is thermal diffusivity alpha. And Kv by Td is called as a dimensionless number. This thermal diffusivity also has got the units of meter square per second. But when you look at these two terms, Kv and Td, what do they speak about? What do they really tell about? What is the real physical significance of the kinematic viscosity? Kinematic viscosity signifies momentum diffusion rate, momentum diffusivity, momentum diffusion rate or momentum diffusivity. That is how it will signify how thick the hydrodynamic boundary layer will be. Kinematic viscosity of a fluid tells about how thick the hydrodynamic boundary layer or velocity boundary layer would be. I can say that if a fluid has got more kinematic viscosity, for that fluid when it is flowing over a flat plate, the thickness of the hydrodynamic boundary layer would be relatively more. If the Kv value is more, thicker will be the hydrodynamic boundary layer thickness. If Kv value is more, I can say if Kv is more, delta is more. What is the delta? Thickness of the hydrodynamic boundary layer, also known as the velocity boundary layer. Okay. And this alpha, thermal diffusivity alpha signifies heat energy diffusion rate of the through the fluid layers. Heat energy diffusion rate. If kinematic viscosity signifies the momentum diffusion rate, alpha signifies the heat energy diffusion rate. Thus, alpha signifies how thick the thermal boundary layer would be. If you just look at this, there is another boundary layer called as the thermal boundary layer, TBL. The thickness of the thermal boundary layer will be more if alpha value of the fluid is more. If alpha of fluid is more, alpha is a thermophysical property. Just like kinematic viscosity is a thermophysical property, alpha is also a thermophysical property. If alpha of fluid is more, implies delta T would be more. If nu of fluid is more, if kinematic viscosity of fluid is more, implies the thickness of the hydrodynamic boundary layer would be more. Please note that delta and delta T symbols. When T is there, it means it is the thickness of the thermal boundary layer. If delta T is not there, it means it is the thickness of the HBl thickness is denoted as delta. So the relative thicknesses, the relative magnitudes of the thicknesses of hydrodynamic boundary layer and thermal boundary layer would be given by the Prandtl number, because Prandtl number is the ratio between nu and alpha. One of the most significant numbers in convection heat transfer is this Prandtl number, because it is a property. One fluid, one value of the Prandtl number. If PR is greater than 1, if PR is greater than 1 implies nu is greater than alpha, implies delta will be greater than delta T when that fluid is flowing over a flat plate. That means it is comparing, Prandtl number is comparing the relative magnitudes of the diffusion rates of the two different physical quantities. One is momentum and other is heat energy. Okay, Prandtl number is comparing the which diffuses faster. Diffusion means passing through. Which diffuses faster through the fluid? Whether momentum diffuses faster or heat energy diffuses faster, that can be directly given by the value of the Prandtl number. If the Prandtl number is greater than 1, which means nu is greater than alpha, means momentum is diffusing faster than the heat energy. Therefore, the thickness of the hydrodynamic boundary layer will be greater than the thickness of the thermal boundary layer. So, that is how the Prandtl number can directly tell which boundary layer is relatively thicker than the other, whether HBl is thicker or the TBl is thicker. Fine. Now coming to this another important number in the which we talk about the mass diffusion. Which talk about the mass diffusion, that is called as the Skint number. Skint number M silent. Skint number, it is called SC. Skint number, it is ratio between the kinematic viscosity and mass diffusion coefficient D. D is called as the mass diffusivity or mass diffusion coefficient. Mass diffusion coefficient. Mass diffusion coefficient or mass diffusivity, or mass diffusivity defined from where it is defined. Mass diffusivity defined from Fick's law of diffusion, defined from Fick's law of diffusion. Fick's law of diffusion states that the mass flux per the rate of mass flux is directly proportional to the concentration gradient. Fick's law of diffusion states that the rate of mass flux along a given direction is directly proportional to the concentration gradient along that direction. Okay, so from that this diffusion coefficient is defined having the units of same meter square per second. So Skint number is comparing the relative magnitudes of momentum diffusion and mass diffusion. Totally we can say there are three things that are you have to talk about: mass diffusivity, momentum diffusivity, and third thing is the heat diffusivity, heat energy diffusivity. This is alpha, this is nu, this is D. So all the three quantities are having the same units, that is meter square per second. But whereas this is talking about the concentration boundary layer, CBL. Concentration boundary layer means CBL. This is talking about HBL, hydrodynamic boundary layer. This is talking about thermal boundary layer, TBL. This is TBL, this is HBL, this is CBL, this is delta C, this is delta T. Three different thicknesses. Thicknesses of the thermal boundary layer is delta T, thickness of the hydrodynamic boundary layer is delta, thickness of the concentration boundary layer is delta C. So the three different boundary layer thicknesses are signified are given indirectly by these values of D, mass diffusivity D, kinematic viscosity KV, and thermal diffusivity alpha. Okay. So this Levi's number is the ratio between the SC divided by Prandtl number, that is if we just substitute these values there, what is the SC? Nu by D divided by nu by alpha. It becomes alpha by D. So Lewis number compares the heat energy diffusion rate divided by the mass diffusion rate. So answer for the Lewis number is ratio between the Skint number and the Prandtl number, which compares the heat energy diffusion rate or heat diffusivity versus mass diffusivity. I can say if Lewis number is equal to 1, if Lewis number is approximately equal to 1, implies concentration boundary layer thickness is almost equal to the thermal boundary layer thickness. If Lewis number is almost equal to 1 for a fluid, for that fluid, the heat transport and mass transport would occur at the same rate. If the Lewis number value is equal to 1 for any fluid, for that fluid, the rate at which the heat diffuses is equal to the rate at which the mass diffuses. Therefore, the concentration boundary layer thickness is almost equal to the thermal boundary layer thickness if the Lewis number is equal to 1 for any fluid. So that is the significance of the Lewis number. Understand? So the TBL is delta T, HBL is delta, and delta C is the concentration boundary layer thickness. Concentration boundary layer thickness is something connected with the mass diffusivity. How quickly the mass could diffuse, the molecules of any fluid medium can diffuse in a particular direction. That is called as the mass diffusion rate, defined from the Fick's law of diffusion, which says that the rate of mass flux, the rate of mass transfer per unit area, or the rate of mass flux is directly proportional to the concentration gradient. From that law, this mass diffusivity or diffusion coefficient has been defined. Coming to this fifth question, a room contains 25 kg of air at 100 kilopascal and 14 degrees Celsius. The room has a 250 watt refrigerator and 1 kilowatt electric resistance heater. A room is there, insulated room, mind that. It is a room is insulated. Sorry, the air temperature in the room remains constant, yeah. This is an electric heater is there. There is one refrigerator. Refrigerator needs power. This is the refrigerator. This is the electric heater. So there is energy coming in for the running the heater and for running the refrigerator. So how much energy is coming? For the refrigerator is consuming 250 watts and the electric heater is consuming 1 kilowatt. During a cold winter day, it is observed that both the refrigerator are running continuously, but the room temperature remains constant. That means whatever the energy that has been entering, that must leave from the room. That must leave from the Q loss. So this power, whatever the work done for steady state condition of room, from the energy balance, I can say for steady state condition of room. That means the conditions in the room are not changing with respect to time. For steady state condition of room, electric power entering the room, to run heater and refrigerator, must be equal to the heat transferred from the room. Whatever the electric power that has been entering into the room to run the heater and to run the refrigerator, that must be equal to the heat loss from the room. Then only the energy entering, only when the energy entering into the room is equal to the energy leaving from the room. Only when these two are equal, whatever the energy entering in the room in the form of the mechanical power or electric power should be equal to the heat loss from the room. Then only the room can be at a steady state. Energy entering should be equal to the energy leaving. What is the electric power entering into the room? 250 watts plus 1 kilowatt. Okay. Electric power entering room. Electric power entering room is equal to 250 watts plus 1000 watts. That is 1250 joules per second. But the answer has been asked in kilojoule per hour. So that should be multiplied by 3600. 1250 into 3600 because per hour, no. But kilojoule is asked. I have to divide with 1000. So many kilojoule per hour. It should be equal to the 4500 kilojoule per hour. This is the answer. Understand the concept. If this is the room, electric power entering should be equal to the heat loss. Only when both are equal, this room is at a, room conditions are at a steady. For this steady conditions to maintaining, this should be equal to the this. If this is more than this, temperature will rise, keep rising. If this is more than this, temperature keep decreasing with time. But you are maintaining a steady state. That means both should be equal. So answer is 4500 kilojoule per hour. Coming to the sixth question, a radiator on a space capsule. See, here comes the importance of the heat transfer subject. Radiation is the only mode of heat transfer that can be occurring inside the space. See, that is why this subject is very important in the ISRO examination. In the space where there is no medium, the only mode of heat transfer that is possible is thermal radiation heat transfer, because that mode of heat transfer does not require any medium, because it happens in the form of the electromagnetic waves which can travel even through the vacuum. Conduction requires medium, convection requires medium, but radiation does not require any medium, because even in the space also it can happen. That is how we are getting the energy from the sun to the earth. So this question is regarding a space capsule. A capsule is operating inside the space. A radiator on a space capsule must dissipate heat generated inside the capsule by radiating it into the space, while on the bright side of the earth, the capsule sees the earth's radiation and solar radiation. The radiator surface has a solar absorptivity of 0.5 and emissivity of 0.9. Solar absorptivity of 0.5 and emissivity of 0.9. What is the maximum equilibrium surface temperature of the radiator if the maximum heat generated in the capsule is 800 watt per meter square? Earth radiation given, solar irradiation given, Stephen Boltzmann is also given. It's a very important question pertaining to the radiation heat transfer. So for which we have to write the energy balance. In the heat transfer subject, how to write the energy balance is the most crucial central concept of the problem. If you don't understand that how to write the energy balance, you can't do any problem. Here I will write the energy balance like this. Solution I could write like this. There is a space capsule. This is a capsule. Okay, it is operating in space. It is generated. Inside there is a generation. Look at that. What is the heat generated in the capsule is 800 Q generated, because of some reasons, maybe some electrical devices are there or electronic devices are there. That is why it is generating heat, 800 watt per meter square. If A is the area of the capsule, 800 watt per meter square, it is per surface area, it is generating. Inside, the heat is being generated inside the capsule. And also the capsule is seeing the bright side of the earth, and also capsule sees earth radiation and solar radiation. This is the earth. This is earth radiation it is seeing. Apart from that, it is the solar radiation also it is seeing. There are two radiations that are coming, one from the earth, one from the brighter side of the earth, other from the solar radiation. From the sun, it is coming solar irradiation. How much it is given? Solar irradiation is 524. This is 524. From the sun it is coming. And earth, assume earth radiation, it is from the earth brighter side, it is coming 100 watt per meter square. 520 watt per meter square from the sun. Now, what is the maximum equilibrium surface temperature of the radiator? See, capsule also must re-radiate, must give back the energy, must emitted, right? Energy emitted radiation from the capsule, because it has got some temperature. Every body at every temperature emits radiation. Like capsule also is emitting radiation. So the concept goes like this. It is the capsule operating in space, generating heat inside that. Capsule is simultaneously receiving the radiation from the brighter side of the earth. How much value? 100 watt per meter square. At the same time, it is also receiving the solar irradiation of the magnitude of 524. But for steady state, what is the maximum? How do you calculate the maximum surface temperature of the capsule? Emitted radiation from capsule. So my argument, my logic goes like this. For steady state condition of the capsule, if we write the energy balance, it should go like this. For steady state condition means the temperature of the capsule is not changing with respect to time. So the energy balance goes like this. Whatever the energy generated in the capsule plus whatever the energy it is absorbing out of that earth radiation, because some energy is falling on that. Only a certain part of that it is able to absorb, okay? And at the same time, it is also absorbing some solar radiation. Solar absorptivity of the capsule is given 0.5 and it has got an emissivity of 0.9. See, when you compare these two radiations, earth radiation falling on the capsule and solar radiation falling on the capsule, there is a vast difference. What is the difference? Sun being a very high temperature, it is a short wavelength radiation. It is the short wavelength radiation coming from for which solar absorptivity of the capsule is 0.5. Whereas for the radiation coming from the earth, it is a long wavelength radiation for which the absorptivity of the capsule is its emissivity, that is 0.9. From the Kirchhoff's law of radiation, absorptivity is equal to emissivity. So I can say, for the earth radiation falling on the capsule, the absorptivity of the capsule is its emissivity, that is 0.9. Alpha is equal to epsilon, I can take. Whereas for the solar radiation short wavelength, this is the short wavelength solar radiation, absorptivity is 0.5. So whatever the energy absorbed by the capsule from the earth radiation plus from the solar radiation plus the energy generated in the capsule, all must be equal to the energy emitted by radiation from the capsule. From that I can calculate the steady state maximum equilibrium surface temperature of the capsule. So that is the concept I want to apply. So understand? So I would like to indicate it pictorially. Capsule, earth radiation, solar radiation. This is short wavelength. Short wavelength solar radiation. This is the long wavelength earth radiation, brighter side of the earth radiation. This is energy generated. inside the capsule. All that should be equal to the energy emitted by capsule. So I can write the for steady state equilibrium of capsule, energy balance, if you write Q absorbed from Earth's radiation plus Q absorbed from sun's radiation, from solar radiation or sun's radiation, which is a short wavelength radiation. Mind that solar radiation is always a short wavelength radiation because the sun temperature is very, very high, 5800 Kelvin, plus Q generated inside the capsule, all must be equal to the energy emitted by capsule, energy radiated or emitted by capsule. Okay, what is the solar energy absorbed? First let me that is emissivity of the capsule into earth radiation, because alpha is equal to epsilon from the. So for the long wavelength radiation, emissivity of the capsule is its absorptivity. So what is the earth radiation coming? Earth radiation coming is 100. Okay, earth radiation is coming is 100 plus solar absorptivity is 0.5 into 524, of course into area, we will write the area of the capsule, plus what is the energy generated? 800. Okay, heat generated is 800 plus 800 into A is equal to area energy emitted. Energy emitted will be A into sigma temperature of the capsule to the power of 4 into, because by using the Stephen-Boltzmann law says what? The energy emitted from the black body is sigma T to the power of 4 into emissivity of the capsule. Considering the grey body nature for the capsule, because emissivity is equal to E by EB. EB is sigma T to the power of 4. Therefore, emissivity has been given. So, A gets cancelled throughout. Epsilon of the capsule has been given as, epsilon of the capsule is given as 0.9. 0.9 into 100, this is the energy absorbed per unit area from the earth radiation, plus 0.5 into 524, this is the solar absorptivity given, plus 800 is equal to, it is given as sigma 5 into 10 power minus 8 into temperature of the capsule in Kelvin to the power of 4 into emissivity of the capsule is 0.9. While doing this problem, my important logic here is, from the Kirchhoff's law, absorptivity is equal to emissivity. For the solar radiation, absorptivity is 0.5 for the capsule. For the solar radiation, for the short wavelength solar radiation, its absorptivity is 0.5. But for the long wavelength earth radiation, its absorptivity is considered as its emissivity, which is equal to the 0.9. So that logic we have to keep in mind. If you don't catch up that logic, you can't do this problem. That is a very important, crucial logic here is, for the long wavelength earth radiation, the absorptivity of the capsule is considered as its emissivity, which is equal to the 0.9. That is why I multiplied with 0.9 here. Solar absorptivity, anyhow, it has given in the problem, that is 0.5. Okay, so total energy absorbed plus energy generated should be equal to the energy emitted. So, but from that you will get the temperature of the capsule in Kelvin, temperature of the capsule in Kelvin as for 400 K, temperature of the capsule you will get it as 400 Kelvin, that is 127 degrees Celsius is the answer. So this is a very important concept of the problem is total energy absorbed plus energy generated should be equal to the energy emitted by the capsule. Energy emitted by the capsule, I have used the definition of the emissive power of the capsule divided by emissive power of the black body should be equal to the epsilon, because emissive power of the capsule is epsilon into EB. EB is given as sigma T to the power of 4 from the Stephen Boltzmann law. Sigma has been given as 5 into 10 power minus 8. Temperature of the capsule to the power of 4 into emissivity of the capsule is given as 0.9. The definition of the emissivity is also used here in solving the problem. Hello students, I hope you have understood all the questions solved in these YourPedia video lectures of myself regarding the heat transfer subject. And you have to prepare for this ISRO examination. You have to prepare for this ISRO examination based on the concepts I had given you, and try to solve some more questions, similar questions, which most likely to be asked in this, because whatever the questions I have selected, they are of the utmost importance in every competitive examination regarding the heat transfer. So if you are able to solve these all these questions, definitely I hope that and practice some more questions in the similar lines, definitely you would be able to face the examination confidently. So as such, if you want to use these video lectures, if you want to view these video lectures, definitely log on to the YourPedia website or the YourPedia panel. Definitely you are able to get this content and make use of that content for advance for writing the examination confidently and with a good concepts in hand. So wish you all the best. Good luck students. This is Sekhar.